When it comes to the most awe-inspiring spectacles in the cosmos, few can rival a supernova, the explosive death throes of a massive star that not only outshines an entire galaxy, but also sculpts the very essence of the universe around it. Join me as we delve into the profound ways these celestial fireworks shape everything we know and don't yet know about the universe. Cosmic fireworks, the grand finale. When a massive star, many times larger than our sun, exhausts its nuclear fuel, it reaches a critical point where the forces of gravity overwhelm the thermonuclear reactions that have been holding the star together for millions or even billions of years. In a final act of cosmic drama, the core of the star collapses in on itself with incredible force, and within a fraction of a second, it rebounds in a cataclysmic explosion known as a supernova. These explosions are among the most energetic events in the universe, releasing as much energy in a single day as the sun will over its entire 10 billion-year lifespan. To put this mind-boggling figure into perspective, if the energy released by a single supernova were spread evenly across the United States, it could power the country for more than 300 million years. At first glance, a supernova might appear similar to a volcanic eruption on Earth, both involving sudden bursts of energy and the ejection of material from a celestial body. However, the true scale of a supernova dwarfs anything we experience here on Earth. During a typical volcanic eruption, molten rock and ash may reach heights of a few kilometers. In contrast, during a supernova, the outer layer of the star is blasted into space at velocities exceeding 10,000 kilometers per second, equivalent to nearly 1/10 of the speed of light. This means that in just one day, the material expelled from a star can cover distances greater than the diameter of our solar system. But even this staggering figure pales in comparison to the raw power released in a supernova. In the split second that the core rebounds, it converts several times more mass into energy than the Hiroshima atomic bomb. It's crucial to remember that this conversion occurs within a time frame of mere milliseconds, allowing for such unimaginable levels of energy release. It's like squeezing the explosive power of thousands of bombs into a fraction of a second, leaving behind an expanding cloud of debris and a neutron star or black hole in its place. To fully grasp the implications of a supernova, it helps to visualize the sheer scale of the event. Imagine standing on the surface of the sun, which has a radius of about 700,000 kilometers. Even at this immense distance, the star's gravity would be thousands times greater than Earth's gravity. If you were unfortunate enough to stand at the center of the star when it collapses, you would find yourself just a few kilometers from the edge of the neutron star or black hole that forms after the explosion. To put this into perspective, our solar system extends as far out as Pluto, located approximately 6 billion kilometers from the sun. Yet during a supernova, the star's outer layers are ejected at speeds so great that they quickly disperse over distances greater than the diameter of our solar system. In a matter of days, weeks, or months, the supernova blast wave expands beyond the orbit of Neptune, which lies about 4.5 billion kilometers from the sun. And all this happens in less time than it takes for a single human hair to fall to the ground under the influence of Earth's gravity. Such is the extraordinary power and speed of these cosmic events, forcing us to contemplate our place in the grand scheme of the universe. The universe's alchemist, forging elements. Supernovas are the cosmic factories responsible for forging the heavy elements that play a pivotal role in the formation of planets and, crucially, the origin of elements essential for life. As the star's core collapses in on itself, it generates extreme conditions of temperature and pressure, triggering a rapid series of nuclear reactions. These reactions, absent during the star's lifetime due to insufficient temperatures, now produce elements heavier than helium. Iron, often considered the end product of stellar nucleosynthesis, is one such element that can be produced in significant quantities during a supernova. But the story doesn't end there. The extreme conditions created during the explosion drive further nuclear fusion. creating even heavier elements such as gold, silver, platinum, and uranium. These elements, once thought to be solely the domain of fantasy, are instead forged in the fiery heart of supernovas, demonstrating the remarkable capabilities of these cosmic events. It's important to note that the creation of these elements isn't a one-off occurrence. The continuous cycle of star formation, death, and rebirth ensures that the universe is constantly enriched with heavy elements. These elements, once dispersed into the vast expanse of space via stellar winds and supernovae, become the building blocks for new stars and planets. This means that the very stuff that makes up our planet and allows life to flourish was once part of a star that exploded in a supernova. In a way, we are all connected to these distant stellar explosions through the elements that define our existence: cosmic genesis, triggering star and planet formation. The shock waves generated by the explosive demise of a massive star don't just etch their mark on the surrounding nebula. They also serve as cosmic bulldozers, clearing and compressing gas on an enormous scale. This dramatic reshaping of the interstellar medium plays a pivotal role in triggering the birth of new stars and planets. Following a supernova, the intense energy released blasts waves of plasma and radiation outward at tremendous speeds, pushing against the boundary of the nearby molecular clouds. This forceful encounter compresses the cloud's outer edges, creating dense pockets of gas and dust. These regions, known as giant molecular clouds, are the primary sites for the formation of new stars. Within these dense pockets, gravity takes over, pulling together the densest clumps of material. As these clumps continue to attract more and more gas and dust, they eventually collapse and ignite nuclear fusion, giving birth to new stars. It's like dominoes falling one after another, with the initial push from the supernova triggering a chain reaction that leads to the birth of multiple stars. But the process doesn't end there. The leftover material that doesn't form new stars condenses into disks around the newly formed stellar nurseries. This material eventually gives rise to protoplanetary systems, the building blocks of planetary systems. The intricate interplay between the supernova shockwave and the interstellar medium thus orchestrates a remarkable transformation. What was once a stellar graveyard becomes a cradle for new stellar life, highlighting the cyclical nature of cosmic evolution. Galactic architects shaping galaxies. The influence of supernovae extends far beyond individual star systems. They play a pivotal role in shaping the structure and evolution of entire galaxies. Supernova feedback, driven by the energy released from exploding stars, acts as a self-regulating mechanism for star formation within galaxies. As massive stars reach the end of their lives and explode, they inject enormous amounts of energy and heavy elements into their host galaxies. This energy, carried by stellar winds and supernovae, creates large-scale galactic winds that blow material outwards. These galactic winds push against the cold gas in the galaxy, preventing the formation of new stars and regulating the rate of star formation. Moreover, the heavy elements released by supernovae enrich the intergalactic medium, the thin gas between galaxies. This enrichment not only enhances the chemical complexity of the universe, but also provides the raw material for future star and planet formation. Furthermore, supernovae contribute to the grand structure of galaxies by driving the formation of giant shells and bubbles of hot gas. These gargantuan voids stretch hundreds of light years across and serve as clear evidence of the explosive history of our own Milky Way. By studying these galactic-scale features, astronomers gain insights into the past star formation activity and chemical enrichment of galaxies. In fact, the hot gas bubbles found in the vicinity of the galactic center hint at a more violent past when the Milky Way had a much higher rate of star formation. Understanding how supernovae shape galaxies is crucial because it helps astronomers comprehend the coevolution of galaxies and the chemical enrichment of the universe as a whole. Our supernova legacy, a cosmic connection. Our solar system's story is deeply intertwined with the aftermath of a nearby supernova. The remnants of this ancient explosion have played a pivotal role in shaping the conditions that led to the formation of our planetary system. About 20,000 light-years away, the star that exploded, known as SN 1006, was almost certainly a massive blue star. The supernova remnant of this explosion is still visible today, and it offers astronomers a unique window into the immediate aftermath of such an event. Studying the detailed structure and chemical composition of this remnant provides valuable insights into the conditions that prevailed after the star's death. It's believed that the shockwave from SN 1006 swept through the region where our solar system would later form, triggering the collapse of the nearby molecular cloud. This collapse gave birth to the sun and the planets in our solar system, kickstarting our cosmic story. In a sense, we are the legacy of this supernova, forever connected to its explosive past. What's even more fascinating is that the same fate awaits our sun. In about 5 billion years, when our sun exhausts its nuclear fuel, it too will explode as a supernova. While our solar system won't be destroyed in the explosion, the shockwave will undoubtedly reach the inner planets, including Earth, causing significant changes to our planet. But we won't be alone in experiencing this dramatic event. Astronomers predict that within our galaxy, several dozen stars will explode as supernovae over the next few billion years, offering us a unique opportunity to observe these cosmic events up close. By studying the details of these future supernovas, we will better understand the processes that shaped our own solar system's birth and the larger universe we inhabit. As we continue to explore the profound ways in which supernovas shape our world, one realization stands out. We are not merely observers of the universe. We are intricately connected to its every event, including the awe-inspiring death throes of massive stars. Understanding these connections not only expands our scientific knowledge, but also deepens our appreciation for the beauty and interconnectedness of the cosmos. As always, thanks for watching. If you've enjoyed this episode, please hit that like and subscribe button. Keep looking up.